We are going to break down the exact mechanics of physics so you can approach your exams with complete confidence. Today, we are focusing on electric charge, current, and the specific calculations that connect them. By the end of this session, you will be able to visualize how electricity physically flows, measure it correctly, and spot the hidden calculation traps that examiners use to drop student scores. Seeing the invisible mechanics at work inside the wire is how you secure maximum marks across the electricity section. Let's look inside. To understand electricity, we start with the physical circuit itself, specifically the solid metal wires connecting the components. Look at this cross-section of a metal wire. Electric current is strictly defined as the rate of flow of electric charge through this space. Notice the components flowing through the stationary metal ions. In a wire, current is a steady flow of negatively charged electrons. We measure the size of electric current using standard units called amperes, or amps for short. 1 ampere is equivalent to exactly 1 coulomb of charge flowing past a specific point in 1 second. A coulomb is simply the standard unit used to measure a bulk quantity of electric charge. A higher electric current simply means a larger physical quantity of charge is passing through that wire every single second. There is a historical quirk in how we talk about circuits that frequently catches students off guard in exams. This diagram illustrates electron flow. Physically, negatively charged electrons travel from the negative terminal to the positive terminal. But before discovering electrons, scientists guessed charge flows from positive to negative. We call this older model conventional current. Here is your strict exam rule. If a question asks for the direction of current, always state it flows from positive to negative. Examiners will test you on this exact distinction. You need to know that actual electrons flow negative to positive, but the standard exam definition for current runs strictly positive to negative. To put precise numbers to this flow of charge, we use a specific measurement device called an ammeter. As seen in this schematic, there is a strict placement rule. An ammeter must be connected in series with the component it measures. In series means placing it directly into the main pathway, forcing all charge to flow through it. This visual shows the core mathematical relationship for these circuits. Charge equals current multiplied by time, or Q equals I times T. For exact units, Q is charge in coulombs, I is current in amps, and T is time in seconds. In an exam, you may need to find when exactly 8 amps pass through a circuit. First, rearrange the formula to I equals Q divided by T. If 4 coulombs pass in 0.5 seconds, dividing 4 by 0.5 results in exactly 8 amps. Now, watch out for a common trap. Examiners often write current values using a unit prefix, like the milliampere, or MA. A milliampere is 1,000th of an amp. Before you do any math, you have to convert this to standard units. If a question gives you 10 milliamperes, you must rewrite it as 10 times 10 to the power of -3 amps. Finally, look at this image. While formula triangles are helpful for rearranging variables in your head, drawing one on your exam paper as your final answer will earn you 0 marks. You must write out the full algebraic equation. Nailing the math requires you to pause, verify your units, and format your equation properly before committing to an answer. You are now fully prepared to approach complex circuit problems with a clear set of logical steps. You can cleanly separate the physical flow of electrons from the conventional definition of current. You know exactly where to place an ammeter in a series circuit and how to manipulate the charge, current, and time formula. And you know to check for the milliampere conversion trap before you start calculating. By keeping these physical mechanics and rules clear in your mind, you are fully equipped to navigate the electricity section of your physics exam.